Okay, so let's continue. So today we're actually going to be starting a new topic. But to recap where we were, let's figure out what things have we actually learned so far. So we first talked about the regular languages, which are here, and then we talked about context-free languages, which are enclosing that because every regular language is context-free. Then we saw a middle subset in between called the deterministic context-free languages. Then we saw, what did we see? So we saw decidable languages right here. And recognizable form an even bigger subset. And of course, there are some languages out here like ATM bar that are not even recognizable. And we can find an example of a language that's within each of these bubbles, but not in a smaller bubble. Okay, so that's all fine and dandy. And what you can easily show is that most, for some definition of most, languages are not recognizable. So they're outside of even the recognizable class. And by most, I mean any number, 99.999, any percentage of nines that you want, at least that number is not recognizable. Because the set of all recognizable languages, the ones within this subset right here, form a countably infinite set, and all languages across the entire thing form an uncountable set. So that means the languages that are outside here in the outside of recognizable must form an uncountable set. So that's fine in some sense, but it's kind of depressing in that the vast majority of problems that you may want to talk about are not even recognizable. So there's not even a Turing machine to even compute those languages. Now, forget about the strings that are not in the language. Just getting the strings in the language, that's impossible for any Turing machine to do, which is kind of sad in some sense. So what we're going to try to do is, okay, well, we can't really do anything about the languages out here because they're not recognizable. And the recognizable languages, well, they may run forever. A Turing machine may run forever on the strings that are not in the language, which is also something we don't really want. We always want any program that we want to always run in a finite amount of time. So let's talk about the decidable languages. But if we have some algorithm, let's just say we have an algorithm A that runs in big O of, let's say, 2 to the 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 n time, is that really what we would want? Well, clearly this is decidable because we can just simulate for that amount of time, and for any value of n, it's always finite. So this is decidable. So the language of A, so to speak, is decidable. Because there's clearly an algorithm that runs in a finite amount of time, no matter what input you give it. But this is not desired. So, not desired to have such a quote-unquote bad runtime. So, maybe could we just focus on the problems that are that have a much smaller runtime than this? So, a lot of work in the 1960s and 70s sought to figure out, okay, what is a good runtime? So what is a good runtime? What does it mean to have a fast runtime? So the way that we're going to interpret this, good is equivalent to the word polynomial. And what does that mean? This means that the algorithm that we're considering runs in big O of n to the c time for some fixed number c. So as long as it runs in that amount of time, then that's what we're going to consider good. So a quick remark on this. So if we have an algorithm that runs in O of n squared time, this is considered good according to this metric. But a lot of work recently in terms of like big data and things like that don't even want n squared algorithms because they're just too slow. So an example of an n squared algorithm you probably have seen is bubble sort. And as you have probably learned, you should never really use bubble sort for the vast majority of cases because it's just too slow compared to the other algorithms which are in n log n time, for example. So the question of what is really good is changing. So good in a modern sense might be in big O of n log to the cn for some c, for some fixed number c. And there are whole classes devoted to studying problems within these runtimes. But what we're going to focus on in this class is the polynomial runtimes. So we're going to make a definition here, which is a class of languages called time of f of n. So what is this? This is the set of all languages that are decided, so they must be decided by a Turing machine or Turing machines. Yeah, because it's not one Turing machine deciding all problems, but it's by Turing machines that run in big O of f of n transitions. So each transition is going to count against the clock, so to speak, for all inputs of size n. So no matter what input I throw at you, if you are in time of f of n, then you must run in big O of f of n time. So let's do an easy example. So all regular languages are in time n. And why is that? Well, time of n is equivalent to all Turing machines running in big O of n time. But we've seen before that you can just go right across the input, and when you hit the blanks, then accept or reject as necessary. So this does run in big O of n time. So all regular languages are in time of n. And if I remember correctly, I'm not exactly sure, but I think they are equal to the class time n. So there's no non-regular language that's in the time of n class. Yeah, that's true. I remember that result. So it turns out that all regular languages are equal to the time of n class, but proving that is a lot harder than this. But every regular language is certainly in the time of n class. So let's do an example of a non-regular language, like 0 to the n, 1 to the n. Well, what was the algorithm that we outlined before? Well, that was just going across the input and writing an x in a bunch of places. So let's just say we have 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, and then blanks after. So what was the algorithm that we did? Well, what we did was we marked off an x, we went right, and then saw the first unmarked one, and then went back, marked a 0, marked a 1, marked a 0, marked a 1, etc. So each time we're going sweeping across the input and writing an x every single time. So that means that each pass we are going to make 2 x's at most. So that means that the number of sweeps, so to speak, is equal to n over 2. It's not exactly equal to n over 2, but it's roughly that. And because we're dealing with big O here, we don't really care about the constant. So the number of sweeps is n over 2, roughly. And for each sweep, we go backwards and forwards. So one direction through the input, one direction back. So the total runtime is the time per sweep times the number of sweeps. And what's the time per sweep? Well, the input's length is, well, in this case, if we represent n by the number of zeros and ones, then the input length is 2n. The n here always refers to the input itself, the entire input. So n, for our purposes, is the length of the entire 0, 1 string. So the time per sweep is 2n, because we have to go... actually, it's at most this, because it could be less. But it's n to go across the input, and then another n to go back. And then what's the number of sweeps? It's n over 2, approximately. So this is approximately n squared. So this implies that the language 0 to the n, 1 to the n, with n at least 0, is in the class time of n squared. Cool. So, and one thing that you can actually show is that, so I won't actually assign this, but because it's actually a bit harder, is to show that 0 to the n, 1 to the n, the same language, is in time of n log n. But not in, by not in I mean, let me write this a different way. So, but does not have an algorithm running in little o n log n time. And so what does this little o mean? For big O, it just means less than or equal to some constant times the function. Here it means that it's strictly less than any constant times n log n. So if it's asymptotically smaller than n log n, then it cannot belong in that class. So in some sense, n log n is the best it can do. But that's a lot harder to show, and we won't actually get into that. Okay, so let's see. So what are we going to talk about here? Well, we're going to make another definition, actually several more, where we're going to call n time of f of n to be the same as time f of n. So exactly the same definition, except for non-deterministic Turing machines. And what does this mean? This means that all computations run in big O f of n time. So it's not like that one happens to do really well. It's just that all of them run in big O of f of n time. So if you visualize the tree that we did when we converted a non-deterministic TM to a deterministic one, where we had something that looks like this. Remember? So when we had something like this, so then the tree can continue, but the height of the tree is always at most big O of f of n in height. So it can't be any higher than some constant times f of n. Okay, and what are we going to talk about here? Well, the two main stars of the show here are going to be, so I'm going to put them in red, are going to be P and NP. So what is P? This is the union over k at least 0 of time n to the k. So in some sense, the P class represents deterministic polynomial time. Man, I butchered that handwriting. Let's try again. Polynomial time. And you may guess what the NP class is then going to be. It's the same thing, but for n time. And so actually NP is one of the most misunderstood concepts in all of computer science. It does not mean, so I'm actually going to write this because there's actually, people misuse this all the time. So this is not polynomial. So the n here does not mean not polynomial. It refers to non-deterministic polynomial time. So that's what that is referring to. The n represents non-deterministic polynomial time, not deterministic polynomial time. Okay, so what can we say about these two sets of languages? So if you have any problem that runs in a polynomial time, deterministically, it belongs to P. And if it runs in non-deterministic time, non-deterministic polynomial time, then it belongs to NP. So what can we say about P and NP? And it turns out we can say something. So it turns out that P is a subset of NP. So any problem that you can run in deterministic polynomial time, you can certainly run in non-deterministic polynomial time, because you can just simulate the deterministic machine and you don't even need non-determinism in that case. So every polynomial time problem in P is also in NP. So then the thing you may want to know is there some language L that belongs to NP but not P? And this is where we get from we know the answer to we don't know the answer. So this is actually a very wide open problem called the P versus NP problem. So we don't know whether there is some language L that's in NP but not P. If you can find one, so here's where you can use your entrepreneurial skills or to try to win some money. If you can find such a language, then or prove that it doesn't exist, then you'll earn $1 million, believe it or not. So yeah, so it's been wide open since the 70s, and it's unlikely to be resolved soon, but most people believe that there is such a language L, and there's evidence, and we may talk about this at some point, of what such a language might be, but proving that it is impossible for any deterministic algorithm to work is, for a non-deterministic polynomial time algorithm, is just, we don't know the answer. So why are we even talking about NP? So you could think about NP as non-deterministic Turing machines that run in a polynomial amount of time, but there's actually a much easier way to think about NP. So let's just talk about that. So another perspective that we're going to talk about for the rest of the class of NP. So what we're going to talk about here is something called a verifier. So a verifier for a language L is a deterministic algorithm. It's just some algorithm that runs deterministically. There's no requirement on how fast it runs. So let's see. Well, then how can we phrase this? So what is this verifier? So I'm going to call it V. So it's a deterministic algorithm, but it must have some property. So what does this verifier actually do? So what it is if we can define the language L in a different way as the set of all strings in sigma star, such that there exists a string C such that V accepts the pair WC together, then we say that V is a verifier. So what is this C string? So this thing is called the certificate. So a way to think about it is you're presented with an input, and C is kind of like the proof that W is in the language L. So if W is really a string in the language L, then C is the proof that it really is in there. So you could just run some algorithm if there happens to be one for L, and that would be the proof. But the verifier will take the input string W and a certificate string, where the certificate is basically just the proof of why that string W is in there. So a way to view NP, so NP is also defined as the set of all languages with polynomial time verifiers. So if you have a polynomial time verifier for a language, then NP is, then that class is, that language is in NP. So let's talk about an example of such a language in NP. So we're going to put on our graph theory hats. So let's let G be a graph. So it has vertices and edges. So if you happen to not remember, these are the vertices, V are the vertices, and E are the edges. And let's just say that we have a particular graph in mind right here. So the points are the vertices, and the lines connecting them are edges. So let's just say we have this, and then maybe we have a more complicated graph like this. And then maybe we'll connect these or something. So I just made a random graph here. So let's see. So what we are going to talk about here is something called a K-clique or click. There's no consensus on how it's pronounced, but most academics pronounce it as clique, so I'm gonna pronounce it that way. So I'm actually gonna add one more edge into here so that I can demonstrate this. So a K-clique is a complete subgraph of G with K vertices. So, for example, if I highlight this subgraph right here on these 4 vertices, so you can see among these 4 vertices and the edges that I highlighted, every single possible edge is present among those vertices. So because there are 4 vertices, the total number of possible edges in this case is 6. And there are 6 edges that I highlighted, so therefore this is a 4-clique because there are 4 vertices involved. And if you highlight any particular edge, let's just say this one right here, well, among those 2 vertices, that's every single possible edge is present because there's only one possible. We don't allow loops or multiple edges here. So this is a 2-clique because there are 2 vertices involved. And I'm sure we can find a 3-clique in this particular case. So here's one. So among these 3 vertices, every single edge is present because that they're all there. and we have 3 edges. So this is a 3 clique. And then, why would you want to learn about such a problem? Well, you may want to find, let's just say, a group of friends who happen to all know each other and are friends with each other, or maybe don't know no one knows anyone else, and you want to invite as many friends as you like. So then you want to find among your friends where the friends are the vertices and the edges represent friend connections that happen to exist. You want to find the largest clique among inside that graph. So let's see. So what can we say about this problem? So the clique problem, the clique problem is the set of all graphs with an integer k such that G has a k clique. I think I got that right. Let's see. I'm looking at my notes just to make sure I got the language correct. And yep, so I have the language correct. So what we would want to do is, in some sense, to find the largest k such that G has a k clique. So this is a decision problem in some sense. So on input GK, what we can do is, what we would want to do for any algorithm is accept if G has a k clique and reject otherwise. Okay, so what would a what would a algorithm for this problem look like in terms of a verifier? So if I give you a graph and I want you to tell me, I tell you there's a 4 clique in there, and you probably don't believe me, what would I have to show you in order for you to be able to verify that the graph indeed has a 4 clique? Well, if I tell you what the 4 vertices are in this graph, then you can verify that all edges are present. So what could a verifier do? So the input W is the graph G. Let's see, did I get that right? Yeah. The W is the graph G, and the certificate string, so remember C is the certificate. So C here is going to be the set of, actually graph G and integer K. Because with every graph there has to be an associated integer K. So C, what would be the proof that the graph G has a K clique? Well, I can just show you the K vertices, the set of K vertices. And then what would the verifier do? So the verifier will check if all possible edges among those K vertices are present in G. So in this graph, if I tell you, I'll highlight them in green. So if I tell you there's a 4 clique, and I tell you these 4 vertices, well, not all possible edges are present. So then you should say, no, that's not an example of a 4 clique. So then what I would have to do to try to convince you that it really is in there is to pick a different set of K vertices. So let's just say these ones in the middle, and then the verifier can go and say, yeah, all possible edges are present, so therefore I will accept at that point. So the verifier is just a deterministic machine that runs in a polynomial amount of time for NP purposes. and checks using this certificate. So C is kind of like the proof that the input GK really is in clique, or whatever NP problem we'll talk about. So let's see, well, what is the runtime of this? So the runtime, so if we want to make sure that it's a polynomial time verifier, we need to make sure it runs in a polynomial amount of time. So what is the runtime here? Well, is to look at all n choose 2 different, oh, oops, not n, sorry. It should be all k choose 2 different pairs of vertices to see if an edge is present. And edge is present. And, well, what is k choose 2? Well, is at most k squared. And we know that k can't be more than the number of vertices because, well, the entire graph could be a clique, but you don't need any more than that. So this is at most n squared. Well, n squared is certainly a polynomial in n, where n here in this case is the number of vertices in G. So this actually tells us that the clique problem is in NP. Because the verifier here in this case runs in a polynomial time in the size of the input, which is the number of vertices in G. Well, it's actually, n is the number of vertices in G. Well, it's actually more than that because the edges are going to count and the integer itself is going to count. So it's actually slightly less than n squared, but in terms of n being the size of the whole input versus just the number of vertices. But we usually just leave all those details out. So, but it certainly runs in a polynomial amount of time. That's all that matters here. So clique is in NP. And it's an open question, because it's the P versus NP problem, as we'll see later at some point, whether, if I can spell, clique, it's open whether clique is in P or not. So we don't know the answer to that. And it's most people believe that it's no. In fact, I don't believe it's in P either, but we don't know the true answer to that because there's no proof of it. Okay, so then what you may be thinking is, okay, well, can we get a deterministic algorithm for clique that runs in polynomial time? So I'm going to, instead of writing polynomial out over and over and over, I'm just going to abbreviate it to poly to make it easier. So here's an algorithm. So what we can do is try all possible subsets of size k. And what we can do is and check if each is a clique. And we can certainly do that just by testing all possible subsets. Well, what's the runtime of this? Well, the number of possible subsets is n choose k. If we have n vertices and k is the number we're given, so n choose k times, well, it's k squared roughly. So it's at most this. So k squared is what we got before. And, well, what is n choose k? Well, you can show that's at most n to the k times k squared. Well, the k squared is at most n squared, so this is at most n to the k plus 2. So then you may be thinking, okay, great. Well, isn't that a polynomial time algorithm? Because is n to the is some number, and so that's good. That's a polynomial time algorithm. So you may be thinking, well, why did it take hundreds and hundreds and hundreds of computer science, decades and decades of research to be able to figure out whether clique is in P, and they haven't yet, when we just proved it in 5 minutes that a clique is in P? It turns out that this is not true. So the constant here where we talked about O to the N C, the C here has to be what is called a universal constant. Universal constant. So no matter what input I feed you, that C will never change. Well, here, in this case, for the clique problem, the K here is part of the input. And so the runtime, so to speak, is dependent on the input itself in terms of the exponent. So if it happened to be like n to the 3 or whatever, then that would be a polynomial time algorithm. But it's not here because this K could be anything. I can feed in whether a graph has a 50 clique or whatever. So this is not a fixed, there's no universal constant here that this runs in. So unfortunately, this is not a polynomial time algorithm. Well, you may be thinking, well, okay, that proves that it's not in P. But hold on. That does not mean that this is the only possible algorithm that could ever happen for the clique problem. There could be a totally different algorithm that runs in polynomial time, but we're not going to be able to talk very much about that because there hasn't been any much progress in terms of getting this down to polynomial time. So what we're going to do is we're going to start talking more about the class NP next time, so I'll see you then.